wish I had friends.
Hey,
Yes?
give me your list money.
Wait, but all I have are these credit cards.
That'll do it.
Yeah.
Do you want to stop getting bullied?
Yes?
Then you need to learn quantum mechanics.
Okay. So, you want to learn quantum mechanics. Well, luckily for you, I might just be able to teach you a thing or two. See, you can tell I'm smart because I'm all dressed up. Now, quantum mechanics can seem a little counterintuitive at first because it contradicts many of the basic laws that we deal with in classical physics. That's why it's important to differentiate between the two. So what is quantum mechanics? Well, quantum mechanics is the field of physics which describes particles in the molecular and the submolecular realm. This includes things like atoms, photons, and electrons. At this level, many of the equations found in classical physics no longer apply. In classical mechanics, if we know about an object's past, like how fast it's moving in what direction, we can determine exactly where it will be in the future. This works both ways. If we know where an object currently is and all the information about it, we can determine where it was in the past. However, quantum mechanics is a little bit stranger. In quantum mechanics, objects aren't simply particles nor waves, but instead a combination of both of them. Even if we have complete knowledge of the past, we can only make probabilistic predictions of the future. The true outcome is impossible to predict. For example, if we have two completely identical uranium atoms, they are more than likely to undergo radioactive decay billions of years apart. In classical physics, dynamic variables, such as velocity or energy, can be measured exactly, only have one value, and with these values you can determine the object's exact trajectory. Furthermore, in classical physics, particles and waves behave differently, whereas in quantum mechanics, everything you deal with is considered a hybrid of the two. In quantum mechanics, each particle possesses a wave function, and this wave function contains all the information that we know about a particle. As time passes, the wave function itself changes, and these changes to the wave function change the probabilities of a particle, such as having a particular position or momentum. Instead of dynamic variables, Schrödinger's version of quantum mechanics uses things called Hermitian matrices to represent the observable quantities of a particle. All of the dynamic variables found in classical mechanics, such as position or momentum, have a matrix as a counterpart. The eigenvalues of the matrix are what determine the value of the corresponding variable. Due to all these distinct differences, Newton's second law, force equals mass times acceleration, no longer applies, and is instead replaced by something called the time-dependent Schrödinger equation. The difference this has on macroscopic objects like people, who have octillions of atoms within them, is negligible, so we can view them under the classical physics lens for all intents and purposes. Because of this, the wave function for such large objects has an extremely short length, which results in the quantum calculations being almost identical to those you would arrive at using the properties of classical physics. Quantum physics only plays a significant role when examining objects either on the atomic scale or smaller. Now this is only a brief overview, so to explain a little bit more about the wave function, I'm going to hand it over to my friend Julian.
Okay, let's take a step back for a second and talk about an electron. A physicist by the name of Louis de Broglie asked himself the question that if a light wave can act as a particle, then can an electron act as a wave? His answer was yes. This concept is called wave-particle duality, where a quantum entity can be described both as a wave and as a particle. De Broglie came up with two equations that describes the relationship between wavelength and momentum, as well as frequency and energy. This was the wavelength lambda is equal to the Planck constant h divided by the momentum p, and frequency f is equal to the energy E divided by the Planck constant h. So now this begs the question, that if an electron could behave as a wave, then what is its wave equation? Classical mechanics dictates that every wave has a corresponding wave equation that describes its motion. So if de Broglie's theory has to hold true, then what is a quantum wave's corresponding wave equation? This is what Erwin Schrödinger sought to figure out.
Well, this is the equation that Schrödinger came up with. Well, he came up with three. These two bottom ones are the more general forms of the Schrödinger equation. The top expression is the time-dependent equation, while the bottom expression is the time-independent equation. Now this expression right here, this longer, more complex-looking equation, is for a more specific case, and you can derive it by assuming that the wave function first equals this general expression, cosine k of x plus omega t plus I times sine of k of x plus omega t. Now this case is for a non-relativistic particle moving in one dimension. And how this works is that by telling the equation about the forces acting upon it, which we can represent by this potential function right here, we can then solve the partial differential equation to get the particle's corresponding wave function. Well wait, where do these equations even come from? How do we even derive these? Where does this equation come from? Well, you see, wait, what's that? We're out of time? Well, I guess that's unfortunate, but I guess it's time to move on.
So, what does the wave function actually represent? Well, if you recall, for this specific example of a non-relativistic particle moving in one dimension, we said that the wave function was represented by psi of x of t was equal to cosine of k of x plus omega t plus I times sine of k of x plus omega t. Now you'll notice that this form of the wave function is the form of a complex number, a plus I times b. Now, the fact that the wave function is complex suggests that it cannot be a measurable quantity. But if you take the wave function and you multiply it by its complex conjugate, i.e. if you take the modulus squared of the wave function, you'll see that this modulus squared is in fact real. But what does this suggest? Well, physicist Max Born suggested that this modulus squared of the wave function represented the probability of a particle in a specific location in space. Now this probability suggests that in quantum mechanics there is a loss of determinism, and that the best we can really do is to predict probabilities. Now this does not mean that quantum mechanics is not deterministic at all, but it does suggest that it is also probabilistic. There are still many conversations and debates regarding if quantum mechanics is truly deterministic or not, and those are generally in the form of the different interpretations of quantum mechanics, such as Copenhagen and many worlds.
Now, advancements in quantum mechanics has led us to this phenomenon known as quantum tunneling, in which a particle has a chance to pass through a barrier. To give you a bit more context, in classical mechanics, if an electron was to encounter a barrier, it would have to go around it. Sometimes, the electron simply does not have enough energy to do that. But in quantum mechanics, the rules are different. They can tunnel. What this means is exactly what it sounds like. The electron can instead, or a small particle, can tunnel through the barrier. Now, this tunneling usually only happens with microscopic particles, like the smallest ones, like the electrons in our computer or the phone recording me. It doesn't really happen with, let's say, the cotton candy stick I'm holding. The possibility of my cotton candy stick quantum tunneling through my hand is so low that I'd have a higher chance of winning the raffle at the festival behind me. Why do I bring up quantum tunneling? That's because unlike me, who does not quantum tunnel through this tree, the electrons in a computer might quantum tunnel through the transistors. What is a transistor? A transistor is the smallest unit within your computer that essentially has one function, to allow or deny the passage of electrons. It is a barrier. But as we discussed earlier, quantum tunneling is when a particle passes through a barrier. This issue now, as transistors are becoming smaller and smaller, is that electrons have a higher and higher chance of passing through them. And when an electron passes through a transistor when it's not supposed to, then we start to have issues. Let's say I'm an electron, I just pass through this transistor here, right? When I'm not supposed to. Now, let's say the guy who the computer wants to run this program, because there was the input that there wasn't supposed to be. So now there's nothing much we can do about it for our classical computers. So instead, what we need to do is develop quantum computers. A quantum computer is different from a classical computer in the sense that while a normal computer uses bits, which are low and high energy electrons, respectively referred to as 0 and 1, quantum computers use qubits. Qubits mean a particle that has 2 quantum states. And you can use a combination of those states, meaning that if we have 4 bits in a classical computer, you would have 16 possible combinations, but the computer can only do one of those combinations at a time. But if you have a quantum computer, if you have 4 qubits, you can store 16 combinations at the same time thanks to superposition. Another advantage of quantum computers is that they would be exponentially faster than a classical computer. Let's say I'm going through Bulbapedia and I want to find my favorite Pokemon, Zygarde. Now, a computer would need a lot of time to go through that. It has 800 entries? Well, a quantum computer could get through that same database in the square root n time. that a normal computer would. And lastly, quantum computers would be able to capture the inner complexity of the molecules that we want to simulate, something that a classical computer cannot do.
Hey, your credit card's running a little low.
I know quantum mechanics now.
What? What?
Hello? Mom? What do you mean the cancer just went away? No, that's great. Thanks. Thanks, quantum mechanics.